Hey everyone, thank you so much for coming, and we are really excited to be here today with you for the Science Week. So my name is Vlad, and I currently lead one of the teams responsible for the ChatGPT pre-training. And today is one of the talks for the Armenian Science Week. I will cover how the technology behind large language models and GPTs work, and basically how we got here. So let's start. The first question probably that we have to ask ourselves is, why should we even care, right? So why should we pay attention to all the development and all the large language models and etc., etc.? Well, obviously, since you are here today, probably for you, this is not one of the questions you're asking yourselves, but still, let's try to answer it. So, over the past several years, we've seen a huge development of models of AlphaGo and AlphaFold capable of performing on a superhuman level of intelligence. There is a recent report from OpenAI basically saying that ChatGPT is used by 700 million people, which is basically a 10% of the world population. And there are a bunch of different LLMs, the ones that write code for you, help you write code, the ones that win Olympiads and are capable of performing at International Mathematical Olympiad, and so on and so forth, right? And probably with all this development, we've seen a lot of applications, products, data companies, and basically a lot of startups being born out of this motion. And usually on these talks, people try to focus on the adoptions, on the products that are here with us today because of the base model. But what's happening is actually there is a core technology at the core of all this movement, right? There is a base model which is a really capable assistant that can follow instructions, that can answer your questions, and without the base model, I'd argue that it is nearly impossible to be able to see all these products and all the development that we are currently witnessing. So what I really want to do today is I want to focus on the base model. Since I'm also working on developing the base model here at Yandex, I thought that it would be fitting to try to explain how the base models work and to basically build up this mental image in your head of what's happening behind the curtains and what's happening on behind the closed doors. And our plan for today is we'll start with the terminology, so we'll try to cover the core concepts behind the models. And this talk is supposed to be kind of an entry level, but I can see a lot of familiar faces here with us today that probably know some of the points that I will try to cover, but hopefully there will be something interesting for you here as well. Then I'll talk about the large-scale training and how to actually train efficiently a large model. Obviously, we would not go deep into the woods since we unfortunately don't have a lot of time, but we'll at least cover the main challenges and the main things that the community is thinking about when trying to work on these models. And then we'll talk about turning base models into assistants, and in the end I'll mention the open problems and some of the resources. So what is the model, right? You have all probably heard like ChatGPT or other models, and I suggest that we think about a model as a collection of two main components. So the first one is weights. Weights are basically just a collection of parameters. So you have a lot of numbers, and those are just basic numbers that you can see here on the slide, like 0.32, -1, or something like that. And inside the model, there's just a lot of these numbers. And this is the first component that I suggest we take into account when we think about the model. And the second component is the computational graph on top of these numbers. So basically, it is numbers and a bunch of operations, a bunch of mathematical operations that we run to actually process the input. And the mental structure of how the computation works is we take an input. The input is just a collection of numbers as well. And we pass it through a computational graph. So we just take our numbers and we do a bunch of operations such as additions, multiplications, subtractions, or whatnot. And we transform the input to the output. And the output is called the model prediction. And I really want to emphasize here that there is no agency inside the model. So similar to how it is popular to think that like model is a black box and we don't know what's happening inside of it, well, this is partially true, of course, but we can think about this process as of just a collection of math operations and a collection of transformations that we run on a bunch of numbers. Yeah, but of course, in practice, this is much more complicated. There are a lot of these numbers that are called weights in modern networks. There are billions and billions of them, and here on the slide you can see one of the most recent state-of-the-art model released by a Chinese company, Qwen, and there are basically 80 billion parameters here. So if you were to store just the weights and just the parameters of this model, you would probably need like a one powerful iPhone or something like that. And so there are a lot of parameters and a lot of complex operations, but we in reality don't really have to think about this today. We can just think of like a lot of transformations. Now let's talk about the training process. So you have all heard, like, we train a model, there is a trained model and something like that. And what is the training process if we've just covered that the model is just a collection of numbers, right? So how do we actually change these numbers somehow? First, I suggest that we focus on a classification problem. Like, let's imagine we have a task where we have to tell whether the image is a cat or a dog. And obviously the network has to work with numbers, so we have to encode our images somehow, right? And to encode the images somehow, the most simple thing that we can do is we can, for example, take values for the pixels, like an RGB or something like that, and just pass the numbers for the pixels through the network. And at the end, the model also have to return a number. So it cannot say like, look, this is obviously a cat, I'm pretty confident in that. It has to tell you a numerical prediction. And in this case, this numerical prediction would be just a probability of whether the image is a cat, which in this case is like 60%, or whether this is a dog. Right? So we have the numerical input, pass it through the model, and we get two probabilities for two classes, with classes being cats and dogs. If we take a look at something more complicated, let's say that now we want to predict a grade for a student. So you're teaching like a math subject at the university, and you want to take some characteristics of a student and predict what the grade the student would receive at the end of the term. And what you can do is you can have a collection of features, age features, for example, describing the student, such as the GPA or the past performance of a student on some task, something like that. And you can have on each iteration of the training process, so on each iteration of the model prediction, you can have B students, so a collection of students. And for every student in this collection, you can have a bunch of features that kind of encode the student. So you have a representation, and you have this representation for every student in your class. And then you just run the computation. So here, these things are called layers. Basically, we just abstract the numerical computations and numerical operations into like a larger blocks of some math operations. For example, a linear layer is just a matrix multiplication, or softmax is something that normalizes the values so they sum to 1. And basically what we do is we have this matrix at first, right, which is B by age. B is the number of students, and age is the features that we have for every student. And we transform this matrix as we go through the model. So first we multiply it by a different matrix and so on and so forth. Then we have to update the weights, we have to update the parameters somehow. So how do we do it? We have to have something called a loss function. Basically, since now we have a prediction of our model, we can see whether we are right or whether we are wrong, and how wrong we are if we are wrong, right? And we have some targets. For example, we have a past data or past performance of students, where we know that the students actually got mark B or like a mark A on the previous iteration of your class. So we have this ground truth data for every student. We have the performance that the student had before, and we can compare the model predictions with the actual data, with the actual ground truth data, and based on this prediction, we can modify the weight somehow. So we just have this thing that is called an optimizer. An optimizer is actually a very complex subject. There is a lot of research going on optimizers and on mathematical properties of how to change the weights of the network based on the predictions and based on the actual targets. But in simple terms, we just have the old weights, we have the predictions, and we can calculate this loss function which tells us how wrong we are, and we just submit everything to the optimizer, and optimizer returns basically new weights. So by doing this multiple and multiple times, what we obtain in the end is we obtain these new weights that better approximate the real data, right? And now that we've talked about the classification problem, let's circle back to the original problem of actually reasoning and completing some texts and try to understand how the language models are actually trained, because we are not here to tell whether the image is a cat or a dog, but we're actually here to output texts. And here on the slide you can see a sentence. There is a collection of English and Armenian words, and we can formulate the problem that we are trying to solve by trying to predict the next word in a sentence. So we just sample a sentence from the internet, we paste this sentence into the model, and we try to predict what's next after this sentence. So basically, we try to predict the next word. This is not exactly a word, this is rather a token. A token can be like a part of a word, a number, a comma, a dot, or something like that. And here on the slide, you can see how the text is transformed into tokens, and you can see that not every word is one token. There are some words that are several tokens. And basically, if you think about it, this is also a classification problem, right? So, but instead of having 2 classes, which is cats or dogs, and instead of having 5 classes for the grades, we now have 200,000 classes, where each item inside one of the classes is the next word. So we basically select over all possible words, what is the next word of our sentence. And if we try to visualize this process, we can imagine of a sentence like the chicken crossed the road that we sampled from the internet, and now we know the actual ground truth data after for this sentence, right? So we know that after the word chicken, there is a word crossed, and after the word crossed, there is the, and etc., etc. So we can just paste the prefix of a text into the model. For example, we can paste the chicken crossed and try to predict the next word. And what the model returns, it returns a probability over all the words in our dictionary. So we have 200,000 words, and the model can say, so the word the is 90% confidence, the word chicken is like 0% confidence, and the word red is 0% confidence as well. And since we have the predictions of our model, which are the probabilities for the next word, and we have the actual next word that we've seen in the text, in the real text, right? We can compare the probabilities of the model with the actual data and see how far we are from the real truth. And based on this information, we just adjust the weights and start again. So let's talk about the architecture. So let's talk about this computational graph that actually helps us to predict and to model the language that we have. Basically, inside modern networks, which are called transformers, there are 4 main components. The first 2 are kind of complementary. Since the model works with the numbers instead of text, so we first have to map the text into numbers, and at the end of the model, we have to do this process backwards. So we have to map the numbers into the text again. But essentially, what we're trying to do is for each input word, we create some sort of a representation, similarly to how we had a representation for an image, or how we had a representation for a student, where a student was encoded with its past performance on exams or something like that. Now we have a representation of a word. But instead, we actually are trying to learn this representation and modify this representation as we go through the model. And there are two main operations that help us with that. And these operations are the attention block and the NMLP block, and we'll talk about them in a bit details in a minute. So let's start with an attention, and to start with an attention, I suggest that we think about the lookup tables first. If you're familiar with basically any programming language, you know about dictionaries or hash maps or whatever it's called in all the languages, and basically it's just a collection of keys and values, and we can look up a value by its key, and we get the actual result stored in the dictionary if the key is there, and we get an error if the key is not there, right? So here the dictionary is apple, orange, and lemon, and if we try to look for apple, we actually get the result, and if we try to look for a banana, we have an error. And now we can think about a soft lookup table, where keys not necessarily have to be stored inside a dictionary. Let's imagine a situation where you walk into the bar, into the restaurant, and you have this query in your head where you're trying to search for something fresh and spicy. Unfortunately, on the menu, there is nothing that is both fresh and both spicy. So there are vegetables that are fresh, there is an ice cream that obviously is not spicy at all, and there is chicken that is spicy. And unfortunately, there is no perfect match for you, right? You have this desire for something fresh and spicy, but you cannot find one dish that satisfies you. So you are trying to create a blend of all the menu items weighted somehow by the relevance score. So if the ice cream is not relevant to you whatsoever, you would not get an ice cream. But if the chicken is somewhat relevant, you might order it, right? So what you're trying to do is basically you have a query in your head which is fresh and spicy. You have keys, and the keys are names and descriptions of the dishes on the menu. And you have values for each of these keys, right? So for each name and every description on the menu, you have a corresponding dish that you can order. And for your prompt, basically for your query, you are trying to select a combination of relevant values. So you're trying to select a combination of menu items that you want to order based on how similar they are to your query. If the chicken is very relevant, then you would probably order like 1 portion or 2 portions or something like that. Since the ice cream is not relevant at all, you would not order it. And this analogy is very similar actually to how the attention works inside large language models. So now when you're trying to encode, when you're trying to create this representation for a word inside a sentence, you can take a look at all the previous words that you've seen in that sentence, and based on the similarity between the previous words and the current one, you can somehow alter the representation for your word. Let's imagine you have a sentence, the river bank was muddy, and you're trying to create a representation, so you're trying to create a vector of numbers for the word bank. And to do that, you have to pay attention to all the words that are there in this sentence. And obviously, you have to pay a closer attention to the word river, because the bank can be a place where you store your money, or the bank can be a place which is like basically on the two sides of the river, right? And to actually understand for the model that the bank in this sentence is related to the water and related to river instead of money, you have to pay closer attention to the word river than to the word muddy, for example. And this is basically your menus and your items, where now each word is a query, and all the previous words are keys and their representation of values. If you think about this in mathematical terms, then you can think about this equation. If you don't know what's going on here, that's totally fine. But I just briefly mentioned that Q here is our query, so the representation of a current word, the keys are the previous words, and by multiplying keys by queries, we basically have this similarity score. So we receive how similar all the previous words in the context to our current word. And then having these similarity scores, which is Q by K, we just take values with these similarity scores. So this is attention. Attention that we currently covered just constructs representations for every single word by taking a look at all the previous words in a sentence and their representations. There is also an MLP. MLP is a much simpler operation. It kind of encodes tokens independently, so it does not have any token-to-token relationships. It's just basically a lot of knowledge stored in the model that you can use to modify the representations for every token that you have. There is a simple diagram for an MLP block, which is like two matrix multiplications and a nonlinearity between them. But there are obviously a lot of complications. So we covered that the model is an attention and an MLP block, and attention MLP multiple times computed on every token. But actually all of these things, they do have numbers inside. So each layer has a number. It has some sort of a matrix or parameters, and you also have outputs of these operations, right? So you have an output of a matrix multiplication, you have an output of something else, and if we take a look at a really small network, which is 100 million parameters, you would see that actually it takes something around 5 gigabytes of memory if we calculate approximately. And 5 gigabytes of memory is not that much, right? 5 gigabytes of memory can fit on every GPU, even on a gaming one. But in practice, we don't have these small networks. We have networks of at least 1 billion parameters or hundreds of billions parameters. And for a network with 1 billion parameters, this is already 30 gigabytes of memory. For even larger network, it is almost a terabyte. And for modern networks such as 235 billion parameters, we can have as much as several terabytes of storage that we need just to store the results of the network, just to store the intermediate computations, just to store the weights, the optimizer states, and so on and so forth. And this is a bit problematic. And this is problematic because modern GPUs, unfortunately, they do not have this memory available. Even the most modern GPUs and compute units, they have something around 40 and 200 gigabytes, but we need to store like several terabytes of data. And to do that, we have to partition, we have to cut the model into multiple pieces, and now we end up with a sort of a distributed system where the model is partitioned across multiple GPUs, it is partitioned across multiple compute units, and we have to coordinate all of these units efficiently to make your training be fast and do not lose quality. And there is a bunch of research, a separate line of research of how to do this partitioning and how to do this distributed training in a very nice way. So basically how to split your model between several GPUs so that your training runs as fast as possible without sacrificing the stability. There is a very complicated diagram on this slide, and you don't have to understand what's going on here because actually it would take us hours and hours to describe how the model is actually partitioned. But this is one line of research nowadays that people are working on, and I encourage everyone who is interested in how to split and partition the model into multiple parts to actually take a look at the resources in the end and see how this is done in practice. Another challenge in training is actually how to do these computations fast. So we covered that computations is a bunch of matrix multiplications, a bunch of additions, subtractions, and you have probably all heard that there are concepts such as GPUs, right? The NVIDIA GPUs that are used to train these models, and they cost like hundreds of thousands of dollars for a huge cluster. But what's so precious about the GPUs? Let's try to cover the GPU model in some of the details. Like basically, we can think about GPUs as a collection of independent compute units. You have something called a streaming multiprocessor, or an SM, and on modern GPUs such as H100 here, there are 132 these streaming multiprocessors that can independently run computations. So they can independently multiply matrices or add numbers or do something like that. And there is also a high bandwidth memory, like this large portion of memory inside a GPU, where everything is stored. So this is the part where the model is stored, and each streaming multiprocessor just communicates with a high bandwidth memory to try to read and write the model weights or the outputs of each layer. Inside every streaming multiprocessor, you have 4 subpartitions. These subpartitions are basically completely equal, and one of these subpartitions is depicted on the slide. So there are 4 of these in every streaming multiprocessor, and there are 132 streaming multiprocessors inside the GPU. And kinda all of them are independent, and they can run a set of operations independently. So what's going on here? Basically, you can see 2 main things. The first one is a tensor core. The tensor core is a special hardware unit that you can use to multiply matrices. And thanks to the structure of a GPU, a tensor core is really fast, and using a tensor core, you can multiply matrices in a really fast manner. And there are also a bunch of CUDA cores. They are highlighted here with FP32, int32, etc. Those are used for arithmetic operations such as additions or subtractions. If we take a look at the specification from NVIDIA, we can see that the compute is at nearly 1,000 teraflops per second. 1,000 teraflops is 1,000 multiplied by 10 to the power of 12, so this is like a really large number of operations with a floating point number in every second. So every second your GPU can run this computation, and you can do a bunch of operations every second on your GPU, and we can think about it in terms of clocks. So similarly to how your computer or how your CPU has clocks that kind of tick, and on every tick over a CPU, you can run some sort of an operation. On a GPU, there is also some sort of clocks which run with 1.7 gigahertz frequency, and at every cycle, this single tensor core can compute a small matrix multiplication. So on every cycle, a tensor core can compute a matrix multiplication, which gives you the ability to multiply really, really large matrices in a fraction of a millisecond. This is why GPUs are so powerful, because you can parallelize the computation and you can run them really fast. And if we take a look at how the memory and how the GPU specifications evolved over time, we can see that there are more streaming multiprocessors from one generation to another, so you can parallelize your computation across a higher degree. There is also higher memory available to you to store the weights, so we got from 32 to 141 gigabytes of memory over just several years of evolution, and there are faster clocks that can allow you to run more operations on each cycle over GPU. Yeah, and the ability to efficiently utilize the GPU and to know how to write your code so that it is efficient and it can run fast is also an important skill if we talk about the large-scale training. We can also think about something called arithmetic intensity, and arithmetic intensity is a fraction of how much of computations you have to run for every byte in your tensor. So if you have some sort of elements, right, you have a collection of numbers, you can see how many operations you have to run for every element inside your tensor. And if this fraction is large enough, it means that you're compute bound. A compute bound is a special term which means that if your GPUs were to run faster, you would end up with a higher performing code. So you can migrate from one GPU to a different GPU and obtain a kernel or obtain the function or code that would run faster. If this fraction is low, which means that you read a lot of bytes and you do not run any computation on the bytes that you read in memory, this means that your function is memory bound and you can only run as fast as the memory works on a single GPU. And unfortunately, on modern GPUs, basically all the operations are memory bound. So you're bottlenecked not in the ability to run these matrix multiplications, but you're almost always bottlenecked in the ability to read and write data into the memory of a single GPU. And to be compute bound, you have to have a lot of operations with numbers for every byte that you read. So let's try to sum up what we know so far, which is how to get a better base model, right? So we covered how the base model is trained, that it has a lot of memory pressures, it has GPUs that it works with, and we have to utilize this GPU efficiently. But how do we actually train a better base model? And to train a better base model, we have to first think about the data. Because if your data is terrible, since you're trying to teach your model to predict the next token, and if like basically the next word in a sentence is problematic or is really bad, you wouldn't end up with a strong model. And there is also a line of research that tries to think about how to collect a really good data that would increase the performance of your GPU. Another thing that we can modify is the architecture. So we can try to modify this computational graph that we have, and we try to modify it so that the model acquires new knowledge in a better way. And for example, modern networks, they don't have exactly MLPs or attentions. They might have mixture of experts or linear attentions or something like that. And if you want to, again, dive deeper, yeah, feel free to join us at the after party and ask some questions about the current architectures. Or you can try to change the optimization process and the training process. So there is this thing called an optimizer that we covered a bit. And this is a highly mathematical and highly experimental field where people try to come up with better optimizers, basically better ways to update the weights and update the parameters of your model, given the prediction and given the reference output. And also, the last thing that you can do is you can try to run the computation as fast as possible so that your training is highly optimized, and in the same time frame you can see and you can feed more tokens into the model. And this is something I'm working on, so this is something we also do here, is we try to optimize the real large-scale training runs across of hundreds of GPUs, so they're efficient and they try to utilize GPUs. Yeah, and if we talk about open source releases, for example, that we have, there are two I specifically want to highlight. So the first one is YFSDP. This is a distributed training framework that's been released almost a year ago, and it allowed to train your models faster on a higher amount of GPUs, up to 20% faster than the solution provided by the Torch community. And there is an open source model called YandexGPT 5, which is kind of small, up to for modern measurements. So it's not like hundreds of billions of parameters. It's 8 billion of parameters, which means you can actually deploy it even on your phone and run it efficiently. And at the time of release, this was a state-of-the-art model on several benchmarks that we care about internally. Now that we covered how to train a base model, that we learn how to predict the next word, right? We have to think about how to actually turn these base models into assistants. So if you open up the ChatGPT tab in your browser, you do not have a model that completes the sentence for you, right? So you don't have this autocomplete that you have on your keyboard when you write a message. Instead, you have a highly performant assistant that can actually talk to you. It can generate complex answers and so on and so forth. But currently, if we take the base model that we trained up to this point that can complete the next token, it would output something like this. So if we have a prompt saying, write a poem about bread and cheese, the model would not actually write this poem. Instead, the model would try to complete this document, because this is something that the model was trained to do, right? It was trained to come up with the next thing to say. So instead of actually writing a poem for you, the model would create a bunch of completions here on the top of the slide that are not useful. Well, first, you can trick the model into actually giving you a poem by transforming your question into to look like a beginning of the document. So instead of writing an instruction, into the model. You can write something like, here's a poem about bread and cheese, and then allow a model to complete this text, so you would end up with the thing you wanted to have. But of course, this is not your experience with ChatGPT and other assistants, right? So you do not write something like, here is a working code, and you paste your non-working code and expect the code to suddenly work, right? So you can communicate with the model. And to do that, on top of the training that we described previously, which is teaching the model how to complete the sentences, we also have to run something called supervised fine-tuning. Currently, this is questionable because there are models that's been released in the previous several months that actually do not run any kind of supervised fine-tuning, and they can work just on the base model. But if we try to run the supervised fine-tuning, what we would do is we would have a bunch of experts. So we would basically have a bunch of human annotators that would complete instructions for us. So we can come up with prompts such as here, write an engaging constructive article for my Morocco travel, something, something. And we can have a human actually write a reference output for this prompt. And we would end up with a collection of this completion. So we would have a prompts, and we would have reference data from the humans that we trust, that these outputs are correct and that these outputs are safe, and this is something that we want. And then we would try to change the weights of the model that we got up to this point a little bit, so the model is better at actually following the instruction. And when we train on these pairs of prompt and completion, instead of coming up with the next word to say, the model would actually learn how to follow instructions. But unfortunately, some annotations are just hard to collect. For example, if we have a prompt like write a haiku in Chinese, it would probably be really hard for you to find a human expert that would be able to write a haiku in Chinese for you just to train your model on this completion, right? And unfortunately, also, if you try to collect documents from humans, you wouldn't be able to perform better than humans. And on some tasks, such as math or code, you would hope that the model would perform better than humans. And up to this point, we just have taken documents from humans. We have taken completions from humans. So the model actually cannot learn how to be like better than a human performance on some particular task. And to unlock this performance, to unlock this capability, you can run reinforcement learning on top of the model. Because instead of collecting complex annotations, so instead of collecting a bunch of haikus in Chinese, you can ask the model to generate multiple completions. So you can write an instruction, generate a haiku in Chinese, and the model can give you 5 different outputs. And for you as a human, it is much easier to say this output is better than this one, so this is definitely haiku and this is not, rather than to actually come up with a haiku yourself, right? And we can have a bunch of different completions, and we can ask humans to like rank these completions and to select only the best performing completions from the model. And when we do this, a lot of times we can actually unlock what's called the reasoning. So we can unlock kind of a thinking chain of thought for the model that would try to solve a complex problem. And to do that, we need something called the reward modeling. Reward modeling is either a new model that we train that tries to approximate what a human would think about this particular completion. So if we take a prompt and 2 outputs from the model and paste them into the model, into the reward model, ideally the reward model would answer which one is better with the same confidence and with the same answer as the human would do. Of course, for some problems such as math or code, we don't have to have a separate model. We can actually run tests to see whether the output is correct or not. And to rank code completions, for example, we can have multiple code completions, and we can run tests on all of these completions and see which completion is better in terms of the number of tests that it's passed. And when we have this reward model, and what we can do is we can continuously sample multiple completions from the model, score them with the reward model, select the best ones, and basically guide the model towards increasing the probability of a better completion. Like we sample to completions, we rank them, and we teach the model to generate a higher ranking completion with a higher probability. And if we do that for a lot of iterations, if we do this with a large enough model, ideally we would end up with a model that can outperform humans on Olympiads and it can solve problems better than us. And yeah, as you've seen throughout this talk, the field is really fast. There's a lot of things going on. People are trying to train models efficiently, run models faster in production, unlock the reasoning performance. There's a mathematical research for optimizers, stability. Of course, people are unlocking new modalities such as vision or videos or speech, something like that. And there's a bunch of research in new architectures. And I think that the best time to start is obviously now. And the best thing you can do is you can read a bunch of papers and see what are the subfields that you like. And hopefully there would be something interesting for you as well. Yeah, and that was it for today. Thank you so much again for joining and supporting the Science Week initiative. And feel free to join the after party and ask questions. Thank you.
Probabilities. How do you obtain probabilities out of model? I mean, model gives you some score, but how can you do it, transfer it to probabilities?
Yeah, thank you for the question. This is actually not a simple question to answer. You can view these outputs as probabilities, because if there are numbers that are normalized to 1, right? You have, like, say you have cats and dogs, so 2 outcomes. If there are numbers that are summed to 1, like 0.6 and 0.4, you can kind of think about them as probabilities. But in practice, unfortunately, you have to come up with some rules, and you have to come up with your own kind of bars, thresholds, to be confident that you can say that something is a probability, that it is correlated with the actual confidence of the model. Unfortunately, usually we cannot do that right now, but we can kind of try to think about the outputs as probabilities, because they look like, this is like something that looks like a duck, and so we can be sure that this is basically a probability. Yeah.
First of all, thanks you for a talk, and I would like to ask a question about limitation of attention-based models. What do you think? What a maximum that can we reach with that kind of models?
Yeah, thank you for the question. There are actually multiple variants of attentions, right? We covered the most basic and the most vanilla one up to this point, and even with this variant, we saw superhuman performance of multiple models that can basically program better than like the vast majority of the population. So I would say the bar is pretty high. And I don't think we've unlocked the scale fully, because we have models that are like 1 trillion parameters, but we do not have, at least open source models, that are like 10 trillion parameters or more, all right? So what if we scale the attention mechanism even further, and we would end up with a better performance? Of course, there are limitations, such as the speed of a generation, and just the number of tokens that we can process, and people are trying to work on that. And yeah, I would say that the problems that require long context reasoning, that actually require you to think efficiently about large documents, and there are actually a lot of large documents in fields we care about, such as medicine, for example. Probably we would need some architectural breakthroughs that we are also witnessing over the past several months, with the field switching over from vanilla attention mechanisms to linear attentions. Yeah. Thank you.
My name is Tim. On some simpler models, if you want to fit your model to your needs, there was an operation where you can cut off the head of the model, fix the weights of the base model, then retrain the model, altering only the weights of your new head. In this way, saving time and money on this, fitting the model to your needs. Is it feasible to do so on large GPT-like models? large language models, or since you have this reinforcement layer on top, this kind of operation is not feasible. Thank you.
Yeah, thank you for the question. If I understood you correctly, basically you're asking, can we take the open source model that has undergo the RLHF or reinforcement learning stage and then run an additional SFT stage on top of the model? Is it correct? Yes. So in practice, I think for us it almost never works, and you would still need to do some sort of RL on top. But there are some ways you can try to basically mitigate the problems that you would end up having. And one of those problems is the model breaking the safety part of your instructions, right? Because usually models that are trained with RLHF, that are trained with reinforcement learning, they learn to follow instructions in a non-harmful way. So if you ask the model like how to create a bump, the model probably would not answer you correctly. But when you run an additional SFT stage on top, you might break this constraint and you might end up with a model that actually tells you and responds to you on your questions, such as like how to create a bump. So there's always this trade-off that you can degrade the performance, but there are some tricks that you can do. For example, you can freeze all the weights as you mentioned and train adapters or something like that. Yeah.
My question concerning to the learning, what is the rule of statistics of the information which we give to the model during the learning process?
Can you repeat the last part, please, of the question?
What is the rule? How big is the influence of the statistics of the information which we give to the machine for learning?
So, like, basically, your question is how much data do we need?
On the
Yeah,
amount of the information which you...
Yeah, that is a great question. Basically, there are some empirical rules. Unfortunately, the field right now is a lot like physics, I would say, a lot like alchemistry of the past, where you just run a bunch of experiments, and instead of proving theorems, you try to come up with empirical laws that would justify your hypothesis. And there are a lot of empirical studies, first of all, that do a thing where you take a model of a given size and you try to train it on different sizes of different data. So you can have a model of 1 billion parameters to be trained on like 1 billion tokens, on 20 billion tokens, 100 billion tokens, and you try to scale these training runs to see whether you have a diminishing returns in the end, right? So basically, how much can you scale the data so there's still a good outcome in terms of training. And there is a bunch of empirical laws that basically tell you you need something like 20 times more data than the model size, and after that there are diminishing returns, or that it is much more useful to train on new data. Like if you have, let's say, 20 billion tokens, it is much more useful to train on 20 billions of different documents than to train 2 times on 10 billions documents, but you would train this 2 times on the same subset of documents, right? So it is always useful to add new information. There's still a signal that's going into the model if you like repeat for multiple epochs of training, but unfortunately all these laws are empirical, and there are people that try to make the connections of these laws with like actual math and optimizers behind them. Yeah, thank you for the question.
My question is about like to finish search, just a second. Like someone write something and program trying to finish and suggesting some options. Are you using some grammar for depend on language and trying to analyze what is the main idea or what is the main word? And by analyzing that meaning, doing some suggestions.
Yeah, thank you for the question. If I got your question correctly, it's like basically, do we somehow change the training process depending on the language at hand, right? So if we train on English or on Armenian, whether the training process changes. This is a very complicated question again. So the general answer is no. The training process stays the same because we don't have any like human knowledge put into the model. We don't have any like rule-based things going on inside the model, right? We just run this computational process for a lot of iterations where we try to predict the next word, but there are multiple complications with that, primarily with Asian languages. For example, in Chinese, there are no spaces at all, right? And what is the word in Chinese, right? What are you trying to predict? What is the completion? And so, yeah, there are multiple questions like that, but in practice, even when you try to adapt a pre-trained model to a new language, you just repeat the same process, and you try to catch up on capabilities, like on this understanding of language, but just scaling the amount of data and just scaling the model, like hoping that the model would be able to figure out all these rules by itself if the model is pretty large and if it sees a lot of data.
I have just philosophical question. A trained model, like LLM model, can somehow hold all the knowledge, up-to-date knowledge. Is there any program to save this knowledge for future generation? I mean, train it and put it in a moon or somewhere in the bottom of the mountain because we don't know what will happen in next year or even next month. We can destroy our world, but somehow we can save today knowledge for future generation.
Yeah, I think you should really pitch this idea to Silicon Valley VCs and get another $10 billion startup. But actually, yeah, I don't know. Basically, this is a really nice idea that the model is kind of compressed state of the world, right? That inside the weights there is a compressed knowledge of all the internet, and having the weights, so having the numbers and having the algorithm to run the model, we can actually get any document on the planet Earth. This is, yeah, really a really nice idea that people are trying to build off. Maybe if we come up with a way to store the weights in a safe place and save the algorithm with these weights, we would be able to somehow use this information. But yeah, I unfortunately haven't heard about like initiatives of sending models to the moon. But there are so many initiatives with large language models nowadays that I wouldn't be surprised.
In regression processes, we have such an idea as over-learning. Do we have such thing also for languages, for GPT-like models?
I would say that no, because whenever the question is like, do we have something statistical, or if we have a law or something of that kind about the model, usually I think the answer is no. Yeah, but if the question is like, how can we interpret the predictions, right? Basically, if we can understand how the model works internally, there are some techniques that can try to take a look at how the weights depend on each other, how the weights are correlated, how they're correlated depending on the output, like what neurons of the neural network is activated depending on the output, and based on that, come up with some sort of an interpretation of what's going on in the model of the internal state. But yeah, in general, I don't think they're something mathematical, again, unfortunately. Just a modeling process of the probabilities, like just model the probability of a next word, and we are good to go.
Do we have any metrics of, like to say, this sentence is close to this one?
Yeah. In short, yes. So since the model is trying to end up with a representation for every word, right? You have this representation that has been enriched and encoded with the view of the previous words, with all the documents. So you have, in the end, you have a really nice representation of a word bank, because you have seen the word bank in a model in like millions and millions of documents. You have seen bank statements, you have seen Wikipedia articles about hastes and something like that. So since you have these vectors in multidimensional space for every word, or you can try to see the distance between these multidimensional vectors in a multidimensional space and take a look at this distance between these representations as of the similarity between vectors. And before, like several years back, maybe 5 years ago, there have been actually a boom of these papers where people encoded different words with embeddings, and they saw that, for example, if you add the representation for if you subtract from the representation of a word king, the representation of the word man, and add a representation for the word woman, the closest thing that you would have is the representation for the word queen. So there's been this like toy examples of how the models operate and how these encodings work. I don't think people actually care about this stuff now, unfortunately. But yeah, this is highly used for search, for example, because when you are trying to search for a document based on the user query, you can try to search for the closest vectors in the multidimensional space.
Hi, my question is, can you use like double precision during the training of the model? Is it has any benefits? Have you tried this or not?
Double precision, you mean like not
64 FP.
like FP32, FP64 or something?
Yeah.
Yeah, there is a huge benefit of actually sacrificing the precision of the weights. Usually people now do not train on FP32, they do train on BF16 or an FP8. And yeah, this is possible. It gives you a lot of benefit because if you circle back to this slide on GPUs, let me just find it real quick. Yeah, so if we circle back to this slide, you see the tensor core, and the tensor core like a special unit that is used to multiply matrices. And on modern GPUs, if you multiply matrices of numbers that are stored not in an FP32 but in BF16, for example, you would end up with a higher throughput. So you would be able to run twice as many operations using this tensor core on numbers that are not in FP32. So yeah, this is definitely possible, and this is something you should do.
Yeah, I just wanted to say thank you for the presentation. You said you're leading one of the pre-training teams at Yandex. What would you say is like some of the biggest problems that you're working on in the next year or two in your pre-training team and just in general, like the pre-training space? Because we've heard some people like Ilya Sutskever say that pre-training is kind of coming to an end. So I'm curious to get your thoughts on, I mean, your opinion on that, and just like what are some important problems that you're working on right now?
Yeah, thank you. I don't think I can share that much, but I will give you my best response. So there is also a similar idea that if scaling does not work, you are scaling the wrong thing. So you can try to scale something different to see that it works better. And I'd say that one of the problems that we are trying to work on right now is scaling, basically, like how to train even larger models and do not sacrifice the stability, because there are multiple problems when you try to scale the model size and when you try to scale the compute cluster. So like with great power comes a lot of instability in model training, and this is something that we are trying to mitigate. All right, if there are no further questions, thank you again for coming here today, and let's enjoy the after party.